Good afternoon, everyone. So, before I start the performance-based seismic design approach, let me talk briefly about the seismic design concept. In seismic design, when we followed building codes, the objective is mainly on the safety. We want to prevent buildings from causing large scale of loss when they collapse during earthquakes. In our seismic design, when we design the normal residential buildings, we do not design those buildings to remain elastic under strong earthquakes, as Dr. Naveed mentioned. If we design the buildings, those normal residential buildings, to remain elastic under strong earthquakes, earthquakes may or may not happen during the lifetime of the building. So if we design like that, in that case, our design may not be economical. So what we do is we design the building to be serviceable under frequent earthquake, low-level earthquakes, but the buildings should not collapse under extreme earthquakes. So here in this graph, x-axis is the lateral displacement or roof drift of the building. Y-axis is the lateral seismic force or base shear. If we design, let's say if we design the building to remain elastic, earthquakes, so if the base shear increased, the displacement will increase linearly as it is shown in the blue line. But we do not design those buildings for elastic base shear VE. We reduce the base shear by R factor. Response modification coefficient are mentioned in the code depending upon the type of the structural system that we used. Then we design for base shear V value. And then we provide the code-specified detailing rules. If we use the high ductility system, we have to provide code detailing requirements. So if strong earthquake happens in to our building, so our design capacity is only V. In that case, if the demand exceeds our design capacity, the members start yielding and then the deformation will increase. So the building becomes a nonlinear response as mentioned in the red line. But in our analysis, we normally carry out the linear analysis, linear static analysis or response spectrum analysis for the base shear, which is divided by R. So our displacement from our analysis is displacement, elastic displacement by R value. So it is very small compared to the actual displacement. And our analysis domain is only in the linear analysis domain, which is shown in the yellow region. And we assume that if we design the members for the forces coming for resulting for V value and provide the detailing according to the code, our building will not collapse under strong earthquake, but the buildings will be serviceable under frequent earthquake. But we do not analyze explicitly for the actual nonlinear response, which is shown in the bubble region. So when we go to performance-based seismic design approach, we can overcome those shortcomings. When we compare with the prescriptive building codes approach, we have to follow the code provisions, and also we cannot evaluate the actual performance of the structural system. We just assume, implicitly assume that our performance will be okay if we follow the code detailing rules. And also there are limitations in the structural systems, permitted structural systems in the code. But if we follow the performance-based approach, we can explicitly evaluate our structural system and also for different levels of earthquakes. If we want to use the structural systems which is not mentioned in the code or which is beyond the code limitations, we can also verify that structural systems are working well under the earthquake loading. And also if we want to use the innovative systems like damping systems or base isolation systems. So we can prove with the performance-based seismic design approach. One last thing is the cost effectiveness in PBD. We can reduce the reinforcement where it is not required. We can reduce that reinforcement, although if the code provisions are required, because we can confidently reduce that reinforcement and provide the additional rebar where it is required, because our analysis is more detailed. For example, in ASCE 7, if we want to use the bearing wall systems in the buildings, in the high seismic zone, there are height limitations. If we want to build the building more than 16 story, in that case, there will be it will not be permitted in the high seismic zone, because the height limit is about 160 feet. So if we want to use the performance-based seismic design approach for the tall buildings like 40-story building, 50-story building with the bearing wall, with the flat slab system, we can prove the performance with the performance-based approach. For example, here, code-based approach, if we want to use, we need to provide the moment-resisting frame and shear walls using as a dual system. And the structural system will use more materials. But if we want to do the performance-based design approach, in that case, we can use the flat slab system with the bearing wall, and we can have the clean structural system, which is favorable to architects. Here, this is a comparison between the code-based structural system and performance-based structural system. Another thing is the omega factors when we design the building members, structural components, which needs to remain elastic or which need to be designed to resist the maximum seismic force demand during the earthquake. We need to use the omega factor, overstrength factor. The overstrength is coming from the material overstrength, and also in our design, we have some safety factors like load factor. We increase the loading with the load factors, and also we have the strength reduction factor, and also our materials. The material strength we use is nominal strength. When we test the actual strength in the lab, the actual yielding strength of rebar will be larger than the strength that we use in our calculation. So those overstrength altogether will provide the additional strength in our structural members. So that overstrength effect is considered with the overstrength factor omega, which is about 3. If we want to design, for example, for this building system, we have the planted columns and transfer system. So we have to design those transfer system for the maximum force demand under earthquake. If we want to do PBD approach, in that case, we can estimate the demand forces in those transfer system explicitly, directly from the analysis without using the prescribed overstrength factors. Another thing is using the damper or the base isolations. So in that case, we can also model those devices explicitly in our nonlinear model and then check the effectiveness of the system. And another thing is the cost effectiveness. When we design the building members, we have to follow the code detailing rules. For example, if we want to use the special reinforced concrete shear walls, we have to follow the confinement rules at the boundary zones. For example, for the boundary zones, we have to provide the 100 millimeter vertical spacings in the code base. But in PBD approach, if we check the axial strain of concrete explicitly, in that case, we can, if the axial strains are less, we can reduce the confinement in the boundary zone of the shear walls. So here on the left side, confinement is very dense, but on the right side, based on PBD outcome, the confinement is significantly relaxed and we can reduce the cost. To conduct PBD, we need additional information compared to the building code-based design. First, we have to prepare the design criteria. That part, okay, we normally prepared in the code-based design as well. but we need to add additional items in the design criteria, considering the nonlinear modeling procedures and also acceptance criteria for different levels of earthquakes. And second one is geotechnical investigation. Geotechnical consultant will provide us the soil bearing capacity, subgrade modulus to use the soil springs in our models. And also it checks the soil type for the seismic loading. If we have the basement wall, we have the consultant will provide the basement wall pressure under earthquake. If the site is on the soft soil and there is a liquefaction potential, they will check the liquefaction effect in the earth soil and also provide the lateral subgrade modulus for the piles, which is reduced due to the liquefaction effect. And the third one is the seismic hazard assessment, site-specific. So that part, it is additional to the normal code-based design. We have to carry out the site-specific assessment for the seismic input. So that consultant provides us the different response spectrum for different levels of earthquake. Normally, they provided as service level earthquake, design earthquake, and maximum considered earthquake. For maximum considered earthquake, they provide the ground motions to be used in the nonlinear time history analysis. If the building is located on the soft soil side, they also carry out the site response analysis to check the amplification of the ground motions due to soft soil. For the tall buildings, wind tunnel test is also important. We have to engage the wind tunnel consultant to carry out the structural load study. For ultimate strength design, normally we use 700-year return period wind load. And for the serviceability check, we use 10-year return period wind load. Wind tunnel consultant will provide us the floor-by-floor wind loads for service level and ultimate strength design. And also they conduct the natural frequency sensitivity study for their wind loads, because our finite element models are not exactly same as the actual building response. When we measure the natural frequency of the building in which are already constructed, they are different from our finite element model. So to consider that effect, the wind tunnel consultant conduct the frequency sensitivity analysis. So in PBD process, there are a lot of consultants, several consultants involved. Architects, structural consultant. If we engage the PBD consultant separately, there will be PBD consultant, and also geotechnical consultant, wind tunnel consultant, PSHA consultant, and so on. So important thing is coordination between different consultants, which is very important. We cannot assume other people know what we know. When we convey the information from one consultant, for example, from wind tunnel consultant to the structural engineer. So in that case, we have to clearly mention that what are the wind loads that we use, what is the return period, and what are the factors, load factors we have to consider, what are the load combinations. We have to clearly mention and convey the information. We cannot assume that another person will know already. So going to the seismic hazard assessment, PSHA consultant provide the response spectra for normally 3 levels of earthquake. One is maximum considered earthquake, which is 2475-year return period, and design earthquake is 2/3 of MCE, and service level earthquake is 43-year return period with different types of damping. So if the building is located near to the fault, for example, 5 kilometers away from the fault, we need to consider the fault orientation in our analysis. For example, if the building is located near to the fault and the fault orientation is 13 degrees from the north to the east, in that case, we have to apply the ground motions according to the fault orientation with respect to the building orientation. So we have to calculate the angle to apply the ground motions with respect to the building orientation in our finite element model. In PBD, normally we check for 2 levels of earthquake: service level earthquake for serviceability check and design the building to remain essentially elastic under that level of earthquake. So the buildings, the structural members will have minor yielding and the structure can be serviceable after the earthquake. But for the MCE level earthquake, our performance objective is collapse prevention. The building should not collapse under extreme earthquake, which has 2475-year return period. The building, although it is not collapsed, the building may or may not be repairable after the earthquake. For PBD overall procedure, first we engage the geotechnical consultant and carry out the assessment, then convey that geotechnical assessment results to PSHA consultant, and PSHA consultant carry out the PSHA analysis. And structural consultant carry out the schematic design for structural member, preliminary member sizes. After they define the preliminary member sizes and provide the model analysis results to wind tunnel consultants to carry out the structural load tests. After getting the wind results, so structural engineer will carry out the wind and service level earthquake design, which is elastic design, because we want the building to remain elastic under those loading. After getting the elastic design results, MCE and linear evaluation is carried out. So in SLE evaluation, response spectrum analysis is conducted, and we do not reduce the base year of the response spectrum analysis like in design earthquake. And we consider R value, omega value, rho value, CD value, all are considered as unity, all are equal to 1. And acceptance criteria, we just check the demand to capacity ratios of members for deformation control actions according to their ductility and also according to their ductility. So for deformation control actions, we allow DC ratios 1.5. But for force control, we allow until only 0.7. And also we check the story drifts limits with the 0.5% limits. For MCE evaluation, we conduct the nonlinear time history analysis using 11 pairs of site-specific ground motions, which are scaled and meshed to the target MCE level response spectrum. And we use the average results of 11 ground motions when we check the results. And in the nonlinear analysis, we consider 2.4% of modal damping and a small amount of relay damping. To classify the actions, deformation control and force control, we have to consider based on their ductility. For example, if the beam flexure response, it has the ductility, so we consider as the deformation control action. But for the shear response of the beam, we cannot consider as deformation control because the response is brittle. So we consider as force control action. So to develop the nonlinear model, we need the backbone curve for the force deformation relationship. That information we obtained from ASCE 41. We are familiar with strength capacity requirements in code-based design. If from our analysis, if the analysis force demand is 500 kilonewton meter in the beam, we have to design that reinforcement to satisfy that strength demand. But we are not familiar with the rotations and the deformation demand. What is the rotation capacity? We do not know. We cannot estimate reliably for the cyclic loading. So normally these backbone curve parameters are obtained from the cyclic loading test. So we use the ASCE 41 parameters in the nonlinear analysis. For shear walls columns, we use the fiber models. For the shear walls, we can model the confinement effect at the boundary zone for the confined concrete, and also in the middle zone, we can consider the unconfined concrete material properties in our nonlinear model. These parts will explain more details in next presentation. For the acceptance criteria, for MCE level, we have to check for global response as well as the local responses. For global response, we check the peak transient drift, which is the maximum drift occurred during the time history. For example, the ground shaking duration is about 25 seconds. So what is the maximum drift occur within that 25 seconds? Residual drift means it is a permanent drift after the ground shaking. So the building may not go back to its original position after the ground shaking. So we check that permanent drift as well, uh, whether it is significantly large or not. If it is significantly large, in that case, the neighboring buildings will be in danger. So we check that one as well. And for the rotations of beams, coupling beams, so we check based on the ASCE 41 limits. For the shear walls, columns, we check the axial strains. For the shear response of the walls or columns or beams, we check with their strength capacity. And also diaphragms, foundation, we design to remain elastic. So when we check the global responses, we have to compare the base shear values with the elastic MCE level response, also with the elastic SLE response. Here is the comparison. The yellow one is the elastic MCE results. If the building remain elastic, this is the base shear, but we do not design to remain elastic in that level. So we allow yielding of the members because of the energy dissipation from the members. The base shear is reduced. So here the green one is the nonlinear base shear. And the red one, the last one is the SLE base shear, which is very small. This is the elastic base shear for service level earthquake. So here, when we compare the yellow and green values, it is the force is reduced about 2 times, 1.5 to 2 times normally. And we check the transient drift. Here is the sample transient drift plot, and average drift is shown in the black color. So average drift is checked with the 3% limit, and individual ground motions are checked with the 4.5% limit. And this is for residual drift. For shear walls and coupling beams, we check the deformations using the axial strains for the flexural response of the shear walls. On the left side, we check the compressive strain of concrete along the height of the wall. And right side is the tensile strain of concrete. Tensile strain of the reinforcement. So we have to check all corners of the wall to check whether the strains are within the limits. And for this is the one coupling beam check along the height of the wall. Average values are shown in black colors. The rotation limit is 0.05 radian for collapse prevention performance level. And in tall buildings, these days we use the outrigger systems. So when we determine the initial sizing of the outrigger columns, we can, if we have the coupling beams in the outrigger walls, connecting the outrigger walls and the core walls, we can check the summation of the shear capacity or the probable shear demand of the coupling beams. That shear demand will be considered as the axial compressive force demand or tensile force demand from earthquake in the outrigger columns. Sometimes we reduce the column size of the outrigger columns in the upper level. Sometimes we have the offset in the columns. So in that case, we can consider that additional moment due to offset by tension and compression strength. To resolve that moment by the tie reinforcement going through the earth slab. And for the diaphragms in the tall buildings, especially podium floors and outrigger floors, we need to model as a semi-rigid diaphragm. Sometimes we use the rigid diaphragm assumption to make the analysis faster in the nonlinear analysis. So if we want to reduce the analysis time, but transfer diaphragms like outrigger floors and podium floors around that area, we need to model with the semi-rigid diaphragm considering the shell elements in those floors. We normally model at least 1 or 2 floors above those zones. If we have the setback floors or if we have the inclined columns in our system, we also need to model as a semi-rigid diaphragm because there will be large in-plane forces in those floors. And another important thing is if we have the setback, we have to check the in-plane shear or stresses in the slabs because the shear walls, shear demand will be transferred to the slab and to the another wall. In foundations, in performance-based approach, We can also check step-by-step analysis results of the time history. So in the foundation, we plot for example, foundation under the core wall. We can plot mx and my of the core wall for each step of the ground motion and end plot. Normally, when we use the load combinations for earthquake loading, we use 130 rule, 130 in 100% in one direction and 30% in another direction. Here, when we plot the core wall moment, we can see that 130 rule is still applicable or not. Sometimes it may be 170 or 150 rule. So we can just estimate the more realistic combination. Here, this is the sample step-by-step analysis results of the foundation under the core wall. So we create the load combinations for each angle of the core wall moment. So we check all cases in the foundation design to cover all angles. So this is just a introduction for the performance-based seismic design. Thank you.